and welcome. It's great to see so many fellow fans of concurrency. My name is Annie, and I work at a startup called Nihilus, where we use Python to build a unified API for email, contacts, and calendars so that you can easily integrate with all the different email providers like Gmail, Outlook, Office 365, Yahoo. And today, I'll be talking about concurrency in Python. We will answer a few key questions. First, what is asynchronous programming? Second, when is it useful? And third, how does it work? We're going to take a bottoms-up approach to understanding concurrency, and we'll explore code for two different implementations of it. First, we'll use plain Python generators to see how we can implement this seemingly complicated concept of concurrency using familiar Python objects. Then we will re-implement the code with Async IO, which is the latest and greatest implementation of concurrency. We will see the similarities and differences in this Async IO version from our original generator implementation. And you will walk away from this talk with a deeper understanding of what's going on under the hood of any asynchronous Python program. Let's dive in. So before we talk about programming, we're going to talk about a restaurant. Welcome to Cafe PyBay. This is the restaurant that we're going to be opening up together. This will be a mental model that we will use throughout this presentation for exploring concurrency. Of course, we want our restaurant to be successful. And in order to ensure that, we need to make some decisions about how to allocate time and resources in order to serve customers efficiently. Here's the basic setup of our fast casual cafe. Behind the counter, there are two tasks that need to be done: taking orders and serving orders. Of course, there are other tasks that go into a restaurant, but for this presentation, we're just going to focus on taking orders and serving orders. The problem we are trying to solve is how to make the restaurant serve customers efficiently. We have a few options for how we can solve this problem. We could throw more stuff at the problem and just open up more restaurants. Or we could hire more staff for our one restaurant and have more people working behind the counter and dealing with the tasks that need to be done. But given the work that we need to do, it might be more simple to have one person work efficiently and multitask between taking orders and serving orders. So I'm sure you're all wondering, why are we even talking about this? Well, if we want our program to do multiple things at once, then we also have to make very similar decisions about how to run our program efficiently. There are a few ways to do multiple things at once in Python. First, you could use multiple processes. These are the processor part of a multiprocessor computer or a multi-core processor. A computer might have a handful of processes, and with multiprocessing, you can run each task in a separate process. Running tasks in separate processes is like running separate restaurants. There's a lot of overhead in terms of resources needed and memory used. Also, the efficiency gain you get by opening up a whole other restaurant might not outweigh the cost of it. Or you could use multiple threads. Threads are resources within a single process. Threads come with more overhead and some difficulty to manage. In our restaurant example, using multiple threads is like hiring more people to work behind the counter. It's more overhead, you have to pay more staff, and there's additional work of communication and coordination between this additional staff. So our third option is asynchronous programming. Asynchronous programming in Python is a vague term, and I prefer to think about it as single-threaded, cooperative concurrency. That's a mouthful, so let's unpack each of these terms. Concurrency. Before we dive into that level of specificity, let's understand what concurrency is more broadly. Put simply, concurrency is dealing with multiple things at once. A concurrent program can make progress on one or more tasks as it runs. The opposite of concurrency is a program running sequentially. Let's go back to our restaurant example. A sequential version is where the person behind the counter considers dealing with a customer from start to finish as a single task. They take an order, wait for it to be prepared, and serve it all before taking the next order. Let's see a demo of this. So right now, they're taking their first order. Now they're waiting for the order to be prepared. They're still waiting, and you can see that there's a customer waiting for their order to be taken. However, they need to serve this first order before they can go take an order. They're still waiting, and there's another customer lining up to have their order taken. Eventually, now the order is finished being prepared, and so now the person behind the counter can serve this order. And finally, they can now continue to take the next order. Sequentially is one task at a time from start to finish. So now for concurrency. Let's see what our restaurant would look like, where the person behind the counter deals with both taking orders and serving orders at the same time. They're going to start in the same position, taking an order. Then when they're waiting for that order to be ready to serve, they see that another customer has arrived and is waiting for their order to be taken. And since they're dealing with both of these tasks at once, they can go up and take this order while they're still waiting for that first order to be prepared. Eventually, by the time they are done taking the second customer's order, the first customer's order is ready to go, so they serve that. Concurrency is dealing with multiple tasks at once. They were able to deal with taking orders and serving orders. Okay, the next term, single-threaded. Now that we know we are going to be dealing with multiple tasks at once, how are we actually going to do this? Single-threaded means that every task runs in a single OS-level thread. You have a single process, and within that process, you have a single thread. And within that thread, you have multiple tasks running. The tasks aren't running at the same time. Instead, one task gets run, gets to a pausing point, and then another task starts running, and so on. But within this one thread, multiple tasks are being run concurrently. Single-threaded seems like it's limiting resources, and thus you shouldn't be able to run that many tasks. But is that the case? Surprisingly, no. And that's because OS-level processes and OS-level threads have overhead. Running multiple processes is like running multiple restaurants. There's more overhead in terms of space, staff, and resources. And running multiple threads is like having more staff behind the counter. There's still some overhead. You have to pay an additional person, and now there's the additional overhead of communication and coordination of staff. Tasks run in single-threaded concurrency don't have these OS-level resources, which makes them lightweight. This makes it possible to run many concurrent tasks within a single thread. Our final term, cooperative. This refers to how the tasks are managed. In cooperative multitasking, tasks control where to pause execution. Multitasking for programs is kind of like multitasking for humans. It's attempting to do multiple things at the same time. In computing, there's two styles of multitasking approaches, preemptive and cooperative. For preemptive multitasking, the operating system can interrupt a running task, pause it, and start running another. The tasks have no control when or if this happens, which means that they can be switched away from in the middle of some complex or important execution. For cooperative multitasking, tasks specify where they will be paused. Let's go back to our restaurant example to see what this looks like in practice. For this example, let's think of the chef in the back as the operating system, who can control when the staff switches tasks. An example of preemptive scheduling could be when the person behind the counter has 3 orders hot and ready to serve, but the chef stops them from serving that and switches them over to taking orders. This is not an ideal time because now all of the pizzas will be cold. For cooperative multitasking, the tasks have complete control over when to pause for other tasks to run. This enables tasks to pause at more ideal times in order to make use of downtime. In our restaurant example with cooperative multitasking, if the person serving orders has downtime, then they can switch and start taking orders to better make use of this downtime. This is useful in programming when our Python programs have downtime, like the downtime involved in I/O operations or network requests. During this time, the program is just waiting for the operation or request to return. With cooperative multitasking, other tasks can make progress in the interim. Okay, that was a lot, so let's recap. Asynchronous programming is single-threaded, which means that all tasks execute within the same thread, and you can support a lot of tasks. It is cooperative, which means tasks control when they pause, and you can better make use of downtime. And it's concurrency, where we're dealing with multiple things at once. Now that we have a better idea of what asynchronous programming is, why should you care? When would you want to use single-threaded cooperative concurrency? It's useful when you have logically separate tasks that you want to make progress on at roughly the same time. There are endless examples of when you might want to do so. So for this presentation, I will just focus on 2 places that my company, Nihilus, uses it. The first spot is pretty widely applicable for web servers. Your server is receiving a lot of requests at the same time, and you want to respond to them in an efficient manner. Your requests also likely involve downtime. The API server is probably asking for something from the database and just waiting for the response. This is similar to our restaurant. We want to serve customers efficiently. Most of the time, the person behind the counter is waiting for the food to be prepared. So why is single-threaded cooperative concurrency the best use here? Because when you are receiving concurrent requests, it allows you to efficiently make use of the downtime inherent to those requests. And during this downtime, other requests can make progress. The second place that we use this is for syncing emails. At Nihilus, we have an API for email, calendar, and contacts. And in order to have more control over the API, we sync all email information from an account's inbox to our databases. That way, we're not beholden to the provider, API, methods, and speed. When we get a new account, there's 2 things that we want to happen simultaneously. We want to sync all of the existing messages in a user's inbox. This can be a lot of stuff, and with provider rate limits, can take quite a while to sync. We also want to be listening for and syncing any new and incoming messages, because it's likely that the user will care a lot more about these new messages than a random email from 3 years ago. We could do these tasks sequentially. We would sync the entire existing inbox from start to finish before syncing new messages. This means users would have to wait quite a while to see any new emails and could be bad customer experience. Or we could do it concurrently, where we start syncing existing emails, then if there's a good place to pause, like an I/O operation, we check to see if there are any new messages that need to be synced, and if so, we can sync those before switching back to syncing existing messages. The implementation of this concurrent version has the same 3 options: processes, threads, and single-threaded cooperative concurrency. We could have used separate processes, one for syncing existing messages and one for syncing new messages. But we have resources that both of these tasks need to share, and that would be difficult to do with multiple processes. We also could have used separate OS threads. But threads are harder to work with because they use preemptive scheduling. And so we use single-threaded cooperative concurrency to be able to sync new and existing mail for hundreds of accounts per process. You're probably thinking, this all sounds kind of magical. How does it actually work? To put these terms into action, we need two things. First, we need functions that are cooperative, functions which can be suspended and resumed. And second, we need an event loop, which does as its name implies and loops over events. In this case, events are the tasks that we want our program to run concurrently. If you're thinking, wait, isn't the event loop a JavaScript thing? Then you're not wrong. If you've ever worked with JavaScript GUIs, then you've already worked with an event loop. Let's revisit our restaurant example. We have two tasks that the person behind the counter needs to do: take orders and serve orders. And in order to do this concurrently, the event loop will be switching the person behind the counter between these two tasks. Let's look at some code. First, we're going to look at an example built with Python generators. A quick refresh. Generators have the yield keyword, and they allow you to declare a function that you can iterate over. Let's check out a small example to see what this actually means. Here is an example where I'm printing out all of the multiples of 3 using a generator. You can tell that get all multiples of 3 is a generator because it has the yield keyword. On line 7, we are calling the generator function that we defined above. When you call a generator function, it doesn't execute it. Instead, it returns a generator object that you can now iterate over to get the values. To get the values from the generator object, you call next on it, and it will return one value at a time. Lines 9 through 11 is where we're doing 10 loops, and in each loop, we're calling next to get a value and printing that value. On the right is the output. The numbers 3 through 30 are the output from these 10 loops. And then beneath that, I call next twice more on the generator to get the next values, 33 and 36. This is just to show that the generator stays in its pause state until you call next on it. So generators are pausable. When you get to a yield keyword, the execution of the function pauses. And we don't have to yield a value. In this example, we were yielding a multiple of 3, but we can just use yield as a way to get the function to pause. This is exactly how we want our coroutine to behave for concurrency. So let's look at our restaurant example, but now implemented in code. There are some imports at the top, and then I use the Python queuing module for no reason other than it's simple to use. Take order is a generator, which you can tell because it has the yield keyword. Let's step through this function. First, it says, while true, basically forever, our restaurant is always open for business. Ask the customer what they would like to order. Let them randomly select one of my favorite foods. Place that order and put it in a queue. When the function yields, it pauses execution and allows the event loop to run another task. And then when the event loop loops back to running this task, it will resume at that yield keyword, which means that it's just going to go back to the top of this while true loop. Serve order is similar. First, it says, forever we will be serving orders. But if there are no orders to serve, yield, so the event loop can run another task, because there's nothing that this task can do right now. For our fast food example, that would be the person behind the counter going to the serve order station, seeing that there are no orders ready yet, and then just going back to take orders. If there's an order, then we'll get it from the queue and we'll serve it to the customer. And finally, here's our event loop. In just 4 lines, we're building an event loop to power our implementation of concurrency. It's pretty cool. This event loop takes an array of coroutines, which you can think of just as a list of the tasks to run. And then it loops over them, calling next on each generator to make it run one loop through. When it calls next, the person behind the counter is switching between tasks. The last line, 33, is how we run our entire program. We're calling our event loop and passing it the list of tasks that we want it to run. For our restaurant example, that's just taking orders and serving orders. I'm going to show you a video of me running this code in my terminal. It goes pretty quickly. The kitchen is just really efficient at the moment. But the two things that I want you to look out for are that orders are being placed. You'll see an all caps placing order, and orders are being served. You'll see some food go by when an order is served. This is just to show you how both taking orders and serving orders is happening concurrently. But if you're writing concurrent code in 2019, you're probably not writing your own event loop, and you're probably not using generators. It's likely that you're using Async IO. So let's look at some code using Async IO to see how it's similar to and different from our generator example. First, a little background. Async IO was introduced in Python 3.4, and it gives us an event loop. Async and await keywords were introduced in Python 3.5, and they create coroutines with this pause syntax. I found it interesting to learn that Async IO and the async await keywords were actually released in different versions of Python, meaning that it's possible, albeit less clear, to use Async IO without async def and await keywords. This separation drives home the distinction behind the two components of single-threaded cooperative concurrency, which are the event loop and the cooperative functions. Let's look at our restaurant example, but this time implemented with Async IO and these keywords. So again, you'll see some imports at the top. And then it's important to note that we use an async IO.queue for our order queue. We'll come back to this later. Here is the take order function, which looks pretty similar to our generator implementation. You'll notice two differences. First, we have async def, and then we have the await keyword. So async def makes the function definition a coroutine, and await suspends the execution of the surrounding coroutine. And it gives control back to the event loop to run other tasks in the meantime. It resumes back at this await when the function that is being awaited returns. And so you can only call await on awaitable objects, like coroutines. So back to our take order function, it flows very similar to how it looks for our generator example, but this time it's using async def and await. Here's the serve order function. You'll notice that it's fewer lines than the generator example. Instead of having the logic for if there's nothing in the queue, yield and continue, we just have this await order queue.get. And that's because the order queue is the special Async IO queue. And Async IO has built that functionality, the yield if it's empty, into its queue. And finally, we have our event loop. We didn't have to create our own event loop. Async IO provides that for us, and we just access it through get event loop. And then we create our tasks that we want the event loop to run with async IO.createTask, and we pass it our functions, which are coroutines. And then finally, we're saying event loop run forever, because this restaurant is always open for business. So Async IO is included in the Python standard library in 3.4 and beyond. And this await syntax is very explicit about when and where functions should pause. It's pretty similar to our generator example of where we had the yield keyword, but this is still a benefit compared with other existing implementations of single-threaded cooperative concurrency, where this yielding behavior is confusingly obscured from the programmer. It also handles the logic for the event loop and exposes a nice interface for working with it. We conveniently didn't have to build our own event loop when we used Async IO. And while all of this feels fancy, it's just another implementation of concurrency. And it's important to remember that Async IO uses the same things under the hood as our generator example. It uses cooperative functions and an event loop. So, to recap, what is asynchronous programming? It is single-threaded, where everything runs in a single OS-level thread. It's cooperative. Tasks can control when they pause, and the OS cannot interrupt them. It is concurrency, where we're dealing with and making progress on multiple tasks. When is it useful? When you have logically separate tasks that you want to make progress on at the same time. It's especially useful when your tasks have downtime, like I/O operations or network requests, where your program is just waiting for that to complete before continuing. In this case, you can make progress on other tasks while you wait. And single-threaded cooperative concurrency works with just two core components: cooperative functions, also known as coroutines, which are functions that can be paused, and an event loop, which manages what task to run next. Questions?